Hello class, welcome to Chapter 3, Probability, and we continue on with our lecture. Here I plan to go over some basic probability rules in this lecture. Let's talk about the experiments which was described in the previous lecture. Let's talk about experiments that have outcomes that are equally likely. What this means is that every outcome of the experiment occurs with equal probability. Okay? So I'll just say every outcome has equal probability. So we can think of some examples, like rolling a fair-sided die, right? If you have 6 sides, if it is a fair die, then you'll have the chance of each side occurring, right, would be the same. So if I roll a die and I want to get a 2, that'll be, the probability is that there will just be one such face, that is a 2, out of the 6 faces, right? So you can't have 2 faces that are number 2, that's what we mean. Then it's going to change the way it is. The probability is set up for that. Pulling a card from a standard deck of 52 cards. So you see again, all the cards are unique. The chance of picking one card, there's only one chance, right, of picking that card, and we have equal probability there because we have 4 suites and 13 cards for each suite. So we have the same card but occurring in those 4 suites. So we have an example there of all outcomes being equally likely. Flipping a coin, again, equally likely to get either a head or a tail, right? All right, now we must remember that just because an event has a certain probability, it does not guarantee that it will happen. Okay? For example, let's say we flipped a coin 2 times. Okay, so let's say flipping a coin 2 times. We know that the total possibilities here would be, so the sample space is HH, HT, TH, and TT, isn't it? So these are all the possible outcomes. But say when you flip 2 coins, you may end up getting TT, which means you didn't see heads at all. Even though we know it is part of the sample space, we don't see it. For that matter, if we flipped a coin, say 100 times, we may still never see heads. Theoretically, that's possible, although practically it seems like, it doesn't seem possible. It's very unlikely, I would say, but it's not impossible, right? So you could get in all those 100 flips only tails, and you may never see heads. So does that mean that what we figured out to be false? Does it mean that it's not equally likely? No, it's again a question of chance. There is that possibility, but the likeliness of that happening is very, very low, right? It's very unlikely that it will happen. So what we say is the theoretical probability, what we figure, right, for example, getting a head would be, 1 out of 2. That's the 50-50 chance. So we are able to give that theoretical probability as a long-term relative frequency of that outcome. Okay. What this means is that when we say theoretical probability, we're saying that this is what we expect to happen. It's not what actually happens. Okay, what we expect. So which means if we repeat the coin toss over and over and over again, we can expect that out of every 2 flips, we will have a head at least 1 time, right? So it depends on repeating this a large number of times. In fact, there's a law of large numbers which says if we keep repeating this for a very large number of times, your theoretical probability will match the actual probability. Okay? So that was a lot of theory there. So we've seen the theoretical probability as the long-term relative frequency. And we saw in the previous lecture the example where we were given a frequency distribution, and from that we derived relative frequency distribution, or the table, and we realized that relative frequency is nothing but the probability. So that's a long-term relative frequency. That's how these two are related. That means your formula that we used, right, probability of an event A occurring, is that it's the number of ways A occurs divided by the total number of outcomes. So then let's explore an example and see what that means. We've seen already an example related to heads, right? Heads and tails. So we'll try something else. Let's read this example. Suppose you roll one fair six-sided die with the numbers 1, 2, 3, 4, 5, and 6 on its faces. Let event E be rolling a number that is at least 5. What is P of E? So think about this. We have E defined to us. So try to write it as a set. I'll write it in words first. Rolling at least at least 5. I'm just clearing again the clutter and just putting the information that we need. So rolling at least a 5. What do you think are the possibilities? At least a 5 means 5 or above, right? A minimum of 5. So the two possibilities we have would be 5 and 6 only, right? Because in a six-sided die, you only have 6 faces. So you can get a 5 or a 6. So that is my E. So if you look at this, the number of outcomes is 2, right? 2 outcomes, 5 and a 6. Now if you go back to your sample space, your sample space is the total outcomes, and we know that we have 1, 2, 3, 4, 5, and 6. Now they gave that information to us, but typically they would not, because it's an understanding that you are familiar with the die. So we have 6 outcomes here. Therefore, if we use the theoretical probability formula, which is the same as your relative frequency, right? If you did that, then we say probability of event E, because that's what they asked us, right? Probability of E is that we get the number of ways E can occur divided by the total number of outcomes. So come back and see how many ways can E occur. It can occur in 2 ways, 5 or 6. And what are the total possible outcomes? We have 6 possible outcomes. So it's 2 over 6, and your fraction is 1 over 3. As always, we try to see if this is a defined value, because probability should always be between 0 and 1. We have that. Now, what we want to understand here is what we found here, 1 over 3, is a theoretical probability. That means in the long run, you will expect, meaning if you repeated this experiment over and over and over again several times, then you can expect your probability to match with this. So that means that if you were to roll the die only a few times, you'd not be surprised if your observed results did not match with this probability. Okay? But if you were to roll the die a very large number of times, you would expect that overall, 1/3 of the rolls will result in an outcome of at least 5. You would not expect an exact 1/3, but the long-term relative frequency of obtaining this result would approach that theoretical probability, this 1/3, okay, as the number of repetitions grows larger. Okay, so I'll just point that out here. Okay. This is theoretical probability. As repetitions grow larger, it will approach the actual probability. All right? So this is really crucial for us. Now let's keep the same problem, and I'm going to define a new event. Let's call it F. F is, let's say, rolling a number that is less than or equal to 4. So now you need to build your set and look at all the possible outcomes. So if it's less than or equal to 4, we have options 1, 2, 3, and 4 because it said less than or equal to. You have to be very careful with the wording. If it simply said less than, then you have to stop at 3. Okay. You see there are 4 outcomes. And of course your sample space, we already discussed. Sample space won't change, right? Because that's the totality of all the outcomes. So we got that. So we have 6 outcomes there for sample space. We've seen that before. So if we want to find the probability of F, probability of rolling a number that's less than or equal to 4, we have 4 outcomes divided by total of 6 outcomes. And reduce this, you get 2 over 3. So this is again the theoretical probability. This is if you repeat this several times, the long-term relative frequency would match with this. Now let's say you are doing, let's say you're rolling a die and flipping a coin. Okay, let's write that. So remember that these are, independent, right? Meaning rolling a die does not impact flipping the coin and so on. It's just these 2 things are done in this experiment. So how many outcomes do you think there will be? How many outcomes? How many possible outcomes? So again, remember, if you have 2 independent events like these happening, when I say events, I meant like an experiment, you have, you can choose to do the tree diagram technique, okay, or you could use the principle, the fundamental counting principle. Either ways, what we see is rolling a die has how many outcomes? 6 outcomes. Flipping a coin has 2 outcomes, heads or tails. Rolling a die would be 1, 2, 3, 4, 5, 6. And the fundamental counting principle says multiply these 2. So from fundamental counting principle or using the tree diagram, whatever you choose to list them out, it tells you that 6 times 2 is 12. So we have a total of 12 outcomes coming from rolling a die and flipping a coin. We call these kind of events as compound events, okay, or compound. If you look at the definition of compounding or compound, what it means is it adds on, right? So there are multiple things. So that's what we're seeing here too. We have multiple things happening. We have rolling a die and flipping a coin. So we have 2 things happening, and so how do we find the probability of a compound event? So what we should do is, first we should list out all the outcomes and then focus on the outcomes from the compound event, and then use the formula of dividing the number of outcomes from the compound event over the total number of outcomes. So I'll give you an example here and then we can take it from there. Okay. So let me set up this example here. Now we have 2 events, okay, compound events, 2 events. I'm just going to use A and B, okay. Now we are rolling a die. Okay, let me write that maybe. And event A is rolling an even number, and event B would be rolling a number less than 3. Alright, we have 2 events here. Now go ahead and rewrite your A and your B using the set notation, okay, as a set. So A would be rolling an even number that we have 2, 4, and 6. If it helps you, you can always keep your sample space, right? You can write your sample space so you know your A can be only a subset of the sample space. You can't have anything that's outside the sample space. That means you didn't exhaust them all, right? So you can have this so that you can see the even numbers 2, 4, and 6. And B would be rolling a number less than 3. Less than 3. It's a strict inequality, which means you can only have 1 and 2. Right? All right. Now, if we said, okay, find probability of A or B, what does that mean? So we have to go back and remember what OR stands for. Okay? So OR evens, if you see the word OR, okay, and obviously the word OR would come only when you have multiple events. You need at least 2 of them. So it is something you will see in compound events. Okay, so for OR events, it means that the event, the outcome, and outcome, here's the definition, is in the event A or B if the outcome is in A or B or in both A and B. Let's read this. An outcome is in the event A or B if the outcome is in A or is in B. Let me write that maybe a little more defined. Or is in B. So you can find that event happening in A, that outcome, or you can find that outcome happening in B, or that outcome could be common to both A and B. That's what this means. You'll understand this better when we actually write this out. Okay. So in this case, if you think of probability of A or B, try to understand this in words. What they're saying is find the probability of rolling an even number or rolling a number less than 3. Okay, so probability of, let me write it out here, A or B is probability of rolling an even number or rolling a number less than 3. Think of this just intuitively. What does this mean? It means that we're okay getting either an even number or a number less than 3, or, because if you see even number and a number less than 3, 2 matches in both these cases, right? So you can find that common value in both A and B, so it doesn't matter. So if you look at A or B, right, the outcomes for A or B would be all of A and all of B, right? So I have 1, 2, 4, and 6. It doesn't make sense to repeat the 1s and the 2s. I mean the 2s, sorry, in this case, just because it appears in A and B. But you know that it's all of A and all of B that will become part of the possible outcomes or the desired outcomes for A or B. Okay, so then I will just write a quick note here. And all outcomes of B. And I'll say don't repeat common elements. Makes no sense to repeat the common elements. Like 1, 2, 2, 4, 6 wouldn't make no sense because it's we're listing all the possible outcomes. We already mentioned 2, so you don't have to repeat the 2. Alright, so this really helps us now because we can see that there are 4 outcomes that can happen here, right, in A or B. So coming over to probability, this is just the event listing, right? Probability of A or B would be number of ways or number of outcomes, right? Just say outcomes. in A or B divided by total number of outcomes. We just figured that A or B has 4 outcomes and the total number of outcomes would be 6, and this comes out to be 2 over 3. Right? So we have the OR situation. We have something called AND situation. And events. So we can describe this as an outcome is in the event A and B. If the outcome is in both event A and B at the same time. You can think about this, right? If you see the word and, you want something to be in A and in B, it obviously has to be found in both A and B at the same time, which means they must have common values in A and B for this to happen. So let's take the same A and B events here that we defined, right? A is rolling an even number and B is rolling a number less than 3. So let me write this out here. Probability of A and B is the same as saying probability of rolling an even number and rolling a number less than 3. So if you think of this, let me write the A and B again. A was 2, 4, and 6, and B was 1, 2, and 3. So the question is, we want to see what numbers overlap or is found both in A and B at the same time. Very obviously, 2 is the only one that overlaps or that is common to both A and B. So if you look at A and B, there is only one outcome. 2 is the only outcome that's possible if you wanted A and B. Therefore, probability of A and B would be one outcome from, so let me write that again in words, number of outcomes or desired outcomes in A and B divided by total number of outcomes. One over 6 would be the probability here because there was only one outcome out of the 6. Yeah. So that was or events and events. We have one more. It's called the complement. So we call them the not events. Okay, another name for this is complement. Okay. Now compliment is when you say something nice about somebody. Okay, this is complement, which means complementary events. One is the opposite of the other. One has things that the other one doesn't have, so they complement each other. All right, so we have ways of denoting this. So I'll just say notation. If A is an event, I'll just say the complement of event A is written as A with a dash, right, or a stroke. We call it A prime. It is read as A prime. Or sometimes the books use the bar, A bar. Okay, so that's the notation here. What this means is it is a set of all outcomes, okay, complement of A means a set of all outcomes that are not in A. Right? That is what we mean by not events. It's not in that. So it's a complement. Complement of A means a set of all events that are not in A. Alright, so let's say we used B previously, so I'm going to use that. B was rolling a number less than 3, right? That's what we used. So if I wanted to find B complement, okay, or in other words, they said find probability of B complement. Okay. I'm using the prime notation. Feel free to use the bar notation based on what you see in the instruction. Now a B prime. So for that, to find the probability, I need to first find B prime. B prime would be everything that is not in B, right? B prime is all outcomes that are not in B, right? For this, let's first list out our sample space once again. Have 1, 2, 3, 4, 5, 6. Sample space is everything that's possible. You cannot have anything outside the sample space as a possible outcome. This is the total possible outcomes, okay? Therefore, your B is rolling a number less than 3. So 1 and 2. Right? Rolling a number less than 3 will be 1 and 2. Therefore, this implies B prime would be all other numbers that are not in B. So if you go to your sample space, and if you remove the values that you see in B, so which means if you take away 1 and 2, you will list all that is remaining. So we have 3, 4, 5, and 6. That is your B prime or B complement. Therefore, probability of B prime would be 1, 2, 3, 4. There are 4 outcomes divided by sample space which has 6 outcomes, which is 2 over 3. Right? So that is your probability of B complement. A deck of cards contains red cards numbered 1, 2, 3, 4 and blue cards numbered 1, 2, 3. Let R be the event of drawing a red card, B the event of drawing a blue card, and E the event of drawing an even numbered card, and O the event of drawing an odd card. Find the probability of the following events. Okay, we'll get to A, B, and C. First, let's try to understand what we have. Okay, if it helps at all, you can always bring in visuals. Okay, so it's like the red card is 1, 2, 3, 4, and the blue cards are numbered 1, 2, and 3. So this might help you to see that we have, these are the only ones we're working with, right? So we have a total of 7 cards. So we want to understand that, and so it'll be easy for us to understand that, instead of listing it, you can see that sample space is 7 outcomes. Notice that I'm not listing them. If I were to list them, it'll be 1, 2, 3, 4 in red and 1, 2, 3 in blue. So it will look like this. Right? Now, if I mixed up the red and the blue, or, if I didn't remember to color code it, you're going to have some confusion there. So we prefer to write the number of outcomes and just use this common picture up there to derive the information we want. So then let's talk about R. Okay, so I'm not going to list them, we're just going to look at the possibilities. R is the event of drawing a red card. So look at how many possibilities we have for the red card. The red card would be 4 outcomes. B is the event of drawing a blue card. So blue card has 3 outcomes. E is the event of drawing an even numbered card. So they didn't just say anything about the color. It's just an even numbered card. So look here and see, in the red we have 2 of them, red, the 2 and the 4, and in the blue we have the 2. So 1, 2, and 3. We have 3 outcomes So if it helps again, you want to do the 2 red, 4 red, and 2 blue. That's another way to list it if you're not using colors to differentiate. Okay. And the last one was O, the event of drawing an odd card. So again, we have 1 and 3 from red and 1 and 3 from blue. We have 4 outcomes. One red, 3 red, 1 blue, 3 blue. Okay. Now, question A says, find the probability of R and E. So it's an AND event. If you recall, AND event means we have to find what is common to both red and common to E. Okay. Now for this, to kind of understand this, it might be better for us to list out, or it might be better for you to list them and then see what's common, or you could come back here and try to see what R and E have in common. So R is drawing the red card and E is getting an even numbered card. Okay, R is red and even numbered. You want it to be both the same in both the sets, or both the events. Okay, so for variety, I'm going to list out R using this. So 1 red, 2 red, 3 red, 4 red. E would be 2R, 4R, and 2B. When you list it like this, it's actually easier to spot what is common. Right? So we have 2R that is common, we have 4R that's common. So if you were to write this out for R and E, it will be 2R, 4R. Okay. You could have reasoned this out just by looking at the numbered cards in the beginning. That's totally fine as well, right? Because you wanted it to be a red and it had to be even, so you can clearly see that you had the 2 and the 4. So it's a lot quicker if you were to reason out like that, but if you were to show the work, this would be what we desire. So there are 2 outcomes that are possible in R and E. So probability of R and E would be 2 outcomes from R and E out of a total of 7 outcomes. Remember? We had 7 outcomes here. So 1, 2, 3, 4, 5. 1, 2, 3, 4 here, and 1, 2, 3 from the blue. That's 2 out of 7. To answer part B says find the probability of B or O. All right. So for B, I'd like to list it out. So go back to what the definition for B was. B was the event of drawing a blue card. So we have 1B, 2B, and 3B as the outcomes. And O was odd numbered cards, right? O for odd. So then you have 1R, 3R, 1B, 3B. Now this is an OR condition, right? B or O, which means we're taking all of B and all of O. We're not looking for only that overlaps, because that will be an AND condition. If it's an OR condition, we are totally fine with taking them all without repeating, of course. If you see something that's common, like 3B is common, 1B is common, you don't want to repeat them. Okay. So just for ease, I'm going to write all the reds first and then the blues. Okay. 1R, 3R. Okay. Then we have 1B, 2B, and 3B. What I did when I was a student was I would list them all and go back and score off the ones that repeated. That way, because I was a little paranoid that I'll miss out on one of the items. So I would write them all and then cancel off the common ones. so that it doesn't duplicate. Anyways, so probability of B or O would be 1, 2, 3, 4, 5. 5 outcomes for B or O divided by total 7 outcomes. Okay. And then the last one was C, which was find P of E prime. E is even numbered cards, right? I'll just say P of E prime. When you have the prime or the complement situation, it's good to have the sample space because it will help you to immediately see what is not in E. So we have 1 red, 2 red, 3 red, 4 red, 1 blue, 2 blue, 3 blue. That's why you had the 7 outcomes, right? E is all even numbered cards. So you have 2R, 4R, and 2B. And we know that E prime is all outcomes not in B, in E. That means in your sample space, it's as if you're eliminating the red, eliminating the 2 red, the 4 red, and the 2B, and collect only what's remaining. So that's why I like to put the sample space up there, so it helps me to collect what I need. So I have 1R, 3R, 1B, and 3B. So it's basically trying to find probability of E prime, which is 1, 2, 3, 4. 4 outcomes from E prime divided by total outcomes 7. Okay. Now, there is another way to also approach this. Now remember, your sample space is all of them, right? So if you have E and E prime, if you combine the outcomes of E and combine the outcomes of E prime, you'll get the sample space, isn't it? So we have something called the complement rule. Okay. And the rule says probability of, let's use the E itself, okay, probability of event E plus the probability of E prime should be 1. 1 is 100%, right? So that means we're saying outcomes or possibilities in E. That's a probability, but I'm talking just about the outcomes. Okay. Will be the outcomes of the sample space. And you can clearly see that, right? Look at the outcomes of E, 2R, 4R, and 2B. Outcomes of E prime are 1R, 3R, and 1B and 3B. If you combine these two, if you took all of this and all of this, you're going to get back the sample space, isn't it? And that is what the complement rule says. Therefore, what we're saying is, well, we could have found probability of E prime by simply rearranging this equation, which is 1 minus probability of E, right? Subtract both sides by probability of E. So 1 minus probability of E. E is 2R, 4R, and 2B, so there are 3 outcomes. So 1 minus 3 out of 7. And if you combine, if you took the LCD this side, 7 over 7, 7 minus 3 is 4 over 7, which is what we got up here, isn't it? So you can do this if you had information on E and find E prime, probability of E prime, from using the complement rule. That will be quicker if you already had found E, probability of E. Okay. And whenever the opportunity presents, we would like you to think about using complement rule instead of listing separately for the prime. Now, through this example, I would like to introduce to you the addition rule. So let's take a look at this problem first. 6 friends at a university are taking classes in statistics or writing. Pamela and Sam are taking statistics. Nandini, Elliot, and Jill are taking writing, and Matt is taking both writing and statistics. If we were to select one friend at random, what is the probability that they would be in either statistics or writing but not in both? Okay, this is interesting. Now, there are ways in which we can express this information, and one of the ways is known as Venn diagram. I just want to introduce that in the concept to you. We won't be using it as much. Just like the tree diagram, a Venn diagram gives you a visual scope of how to represent this information. So what happens in Venn diagram is we actually use circles to represent each set, each group. Okay, so I'll just use, they're typically overlapping circles. They will overlap if you find some overlap, and what I do see an overlap because I see two groups. One is the statistics group and the other one is the writing group, and we are told that math is taking both writing and statistics. So there is an overlap. Okay, so let me write here statistics. I'll keep it purple, and the orange one would be writing. And so we have Pamela and Sam in statistics, and in writing we have Nandini, Elliot, and Jill. Okay, and math is common to both. So you can see that math is part of the purple and is part of the orange. So if you just look at the purple, you have P, S, and M. If you just look at the writing, we have M, N, E, and J, right? So we have that, and this is called the Venn diagram. Now, just like tree diagram, Venn diagram also has limitations. So how do we handle this? For that, we like to write it as a set, perhaps, and try to describe what the sets stand for. So then I would say statistics. I'm going to call it S. This set is statistics, and it has Pamela, Sam, and Matt. And then we have writing. I'm going to call that set as W, that event. Okay. It's M, Matt, Nandini, Elliot, and Jill. All right. Now we're told that if we were to select someone at random, what is the probability that they would be in either statistics or writing but not both? Probability of finding a student who is in either statistics or writing but not both. This is what we're supposed to find. Well, if you look at this, it's pretty intuitive in that if we looked at those who were in either stats or writing but not both, it's very obvious that Matt was the only one who was in both. So we have actually 5 of them, right? For P and S and N, E, and J. So we have 5 of them out of the total 6 who were in either stats or writing but not in both. So you can see that both from your Venn diagram or from your listing, isn't it? So we have a total of 6 students, and out of them 5 of them were in one of these classes but not both classes. So well, there is a formula that we can use to handle these questions. Okay, so what happens is we use the addition rule, which says probability of A or B. Remember we did this? A or B? That will be the same as probability of A plus the probability of B minus the probability of A and B. Notice that this minus part, the subtraction part, helps you to eliminate those who are in both A and B, right? Previously what I told you was, remember to remove any duplicates, right? Because we can have elements that are common to both the groups, both the events, so that when we list all of A and all of B, we might end up listing them twice as a duplicate. So we went around and removed it. Now what this formula does is, it's inbuilt in the formula to take care of the duplicates. So you can feel free to keep the duplicates within, because it's going to take care of that in the end, right? So probability of A plus probability of B minus probability of A and B. would help eliminate the duplicates. Let's try and use the addition rule in this problem. A group of friends take classes at a university in biology, chemistry, and physics. If you selected a friend at random, the probabilities that they take certain classes is given below. The probability for biology class, okay, let me just copy that down, just the pertinent information. Probability of taking a biology class only is 1 over 3. Probability of taking a chemistry class only is 1 over 2. Probability of taking a physics class only is 1 over 6. Probability of a student taking both biology and physics, so B and P, is 1 over 4. And we're asked to find what's the probability of B or P. Okay, so we can use the addition rule. So we have to focus on B and P. These are the two events, right? As per the addition rule, it is probability of the first one, probability of B, plus the probability of the second one, biology plus the physics, minus probability of biology and physics. So let's go ahead and choose the 1 over 3 for the first one. Physics would be 1 over 6. Biology and physics is 1 over 4. So make sure that you compute that. Do the LCD. What's the LCD here? So the LCD here is 12. So times 4, 4, 2, 2, 3, and 3, right? So you want to make all your denominators to be the same. So your LCD was 12. So that's 4 over 12 plus 2 over 12 minus 3 over 12. Now that we have the same denominators, it's 4 plus 2 minus 3. That comes out to be 3 over 12, which reduces to 1 over 4. So that's the answer here. The probability that a randomly chosen friend takes biology or physics is this. So let me write the interpretation. The probability that a randomly chosen friend takes biology or physics is 1 over 4. If the probability of a married couple owning a cat is 0.2, the probability of owning a dog is 0.3, and the probability of owning a cat and a dog is 0.11. What is the probability of a married couple owning a cat or a dog? It's all written in words for us. Let's try to put in our own understanding. Probability of owning a cat, so I'm just going to call it C. So probability is 0.2. P of C is 0.2. P of owning a dog is 0.3. Cat and a dog, C and D, is 0.11. And we're asked to find what is the probability of owning a cat or a dog. So we know this is to do with addition rule. P of C or D is P of C plus P of D minus P of C and D. So go ahead and plug in the values. Minus 0.11. Pull out a calculator and compute this. And that comes out to be 0.39. So you can say the probability of a married couple owning a cat or a dog is 0.39. Now what happens if you were asked to find a different probability? So let me write this question for you then. If A and B are evens, with, they didn't describe the evens, but they're just giving us the probabilities, with P of A as 0.4, P of B as 0.2 and P of A or B is 0.46. Find P of A and B. Okay, so again remember this is a mathematical move because we are still using A or B, the addition rule, which says P of A plus P of B minus P of A and B. But we usually try to find A or B, but here they've given A or B and they're asking us to find A and B. So let's fill in what we have. 0.46 equals 0.4 plus 0.2 here minus, and this is what is missing. Right? And you can totally figure out the missing information by simply rearranging the terms. 0.46 equals 0.6 minus what is missing. Right? I'm going to remove the question mark and just write it as P of A and B. It's just a lot easier that way. Now I want to move the numbers. It's an equation, right? You're just making a mathematical move. This gives me negative 0.14 equals negative probability of A and B. Remember, we should never get a probability that's negative, right? Because your probability must only be between 0 and 1. But all is not lost, because we know that that negative can be countered if we divided both sides by negative 1, because here again you can't give an answer for negative P, right? And so when you rearrange this, you get probability of A and B to be equal to positive 0.14. A bag contains balls with the numbers 1 through 100. If you draw a ball at random, what is the probability that you get a number which is not a multiple of 7? Interesting. You see the word not, you know that somehow there is that complement rule that can be brought in. Okay. And what is the complement rule? If we recall, it said if you added the probability of an event and the probability of its complement, it should add up to a 1. And if you rearrange these terms, you can get these following formulas as well. Probability of A would be 1 minus probability of A prime, and probability of A prime would be 1 minus probability of A. Right. So the last two variations would come in handy if you find it too hard to list one of them. So if it's easier to list the A, you can find A complement by doing 1 minus probability of A, and vice versa. So if you think of this particular problem here, we have our the bag contains balls with numbers 1 through 100. So we have 100 numbers in total. That is your sample space. But then if you draw a ball at random, we're saying what is the probability that it's not a multiple of 7? Multiple of 7 is something we can quickly at least list out. But not a multiple of 7 is so many, right? But we are asked to find what is not a multiple of 7. To answer that, we're going to go ahead and find what is a multiple of 7. So to make it more structured, I'm going to use A to define the event. A would be that you get a number, meaning get a ball which has a number, which is not a multiple of 7, because that's the question, right? So we define the event from the question. If A is not a multiple of 7, what is A prime then? A prime is getting a number which is a multiple of 7. Finding A prime, or finding a list, or listing out A prime, is so much easier. So I'm going to list A prime because it's 1 through 100. It's manageable. So the multiples of 7 would be 7, 14, 21, 28, 35. It's your 7 times table there. 42, 49, 56, 63, 70, 77, 84, 91, and 98. Okay, so we got all of these. Let's go ahead and count how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 outcomes. If you were thinking about, you know, what are not multiples of 7, right? It's 100 minus 14, because the rest of them would be the multiples that are not. So it would be really huge for you to sit and list them. So you can see the importance of using the complement, because probability of A complement is 14 out of the 100, isn't it? Okay. So getting a multiple is this. So what do you think is getting, what is P of A? You can reduce this if you wanted, so that you'll get a reduced answer there too, right? So let's go ahead and reduce this. This comes down to, they're divisible by 2, right? So 7 over 50. So our real interest is in finding probability of A, which is probability of not A, getting a number which is not a multiple of 7. But we know that probability of A is the same as 1 minus probability of A complement. And we just found our probability of A complement to be 7 over 50. And then use the LCD. LCD is 50 over 50 here, right? So 50 minus 7 gives you 43 over 50. And so the probability that you do not draw a multiple of 7 is 43 over 50. So with that, we wind up this lecture. We will continue with chapter 3, and I will see you in the next lecture. See you shortly.